voice or any issues come, then let me know. Okay, I will reach here once. Okay. Good evening all. So today I will be talking about deep water drilling. So as you can see from the crowd, most of the guys are from the second engineering and then second year and then third year and some are from final year as well. So I hope it should be the introductory one only. So I have kept it very elementary for the deep water drilling. Just I want to let you know how the deep water drilling and how the what is deep water drilling and where we call it deep water and where we call it like online drilling and drilling from the jackup shallow water drilling. So I hope my voice is audible to everyone and slide is clear. Just to confirm.
Yes, sir. Yes,
Yes,
sir.
sir.
Yeah. Okay. Thank you. Okay, so types of drilling rigs. So basically, deep water drilling is more about the rig. The rig itself is something to explore. So, like the drilling rigs, types of drilling rig, we start from the land rig, then drilling barges, then we have jackup rigs, semi-submersible, and drill ships. So, jackup, drilling, and the land rig. Jackup and the land rig are all these both are like fixed structure. So we are drilling from the fixed structure from the land or the jackup rig, and jackup rig are sometimes uh, it is attached to the platform as well. So and well from a jackup rig and a land rig are almost identical. So there is not much difference between a well drilled by a jackup rig and a land rig. But there is a limitation with the jackup rig that it cannot operate beyond 500 feet of water depth because you cannot have so much of length of legs of a jackup rig to get support from the seabed. So when this limitation comes, then we go for the floating rig. And the floating rig, we have option of semi-submersibles and the drill ship. So when you go for a floating rig, so floating rig like sea state is not something static, right? So sea state is always in some motion. So if you have gone to some beaches, then you must have seen that the tide that comes on the regular waves that comes on the uh, sea beach. So you can see the sea state is not steady always, and with tide also the sea level changes. So you know that there is high tide and a low tide. So the if you have a floating structure on a seabed, so that floating structure will not be static. It will be like in a high tide, it will be at a very high level from the seabed, and on the low tide, it will be at some lower level. So it is never at mean sea level, right? So that mean sea level is something in between the high tide and low tide, and that is the tide. The tide is like it changes with time, but meaning tide is a gradual thing. Like it will change over like 5 to 6 hours of the day. But beyond that, also one is tide. After that, like whenever the ship is floating, then you have the heave motion of the ship. So the heave motion is very predominant, and this thing will like this of like this. For this only, we have to make so many arrangements for drilling from a floater rig. So heave motion is the motion in the jet direction. You can see like the in the vertical direction, up and down motion. So heave motion is a continuous motion. So whenever the floating rig is at the sea like in the field, so it is moving up and down continuously. And if you have a well at the seabed and your ship is moving, and if you have a yeah, is someone is it noise? Can you check? Yeah, Vijit, I can continue, right?
Yes, sir, you can continue, sir. I guess there was a minimal noise.
Yeah, no problem. Yeah, so this heave motion, am I making sense? Like, is it audible? It is perfectly okay for you, or something needs
Yes,
to be
sir.
changed?
No, sir, it's perfectly audible.
Yeah, okay. Yeah, so like a heave motion is something that is in the vertical direction, the motion in the vertical direction, right? And the rolling, and the rolling is like when it moves in the, you can see the direction, right? So and there is a rolling, pitching. So our main concern is the heave motion, and that I will address further. So you can see that the main important thing was that our rig is not static. So so if it is not a static and we have to drill from the seabed, then some arrangement needs to be made so that this dynamic position and a static seabed is like interfaced. So that is the for that we need to make some arrangements, and that we will discuss further as well. Okay, so station keeping for floating ring. So in a sea, you have always have sea current, wind. So to if you just have a ship on a seabed, and if there is a very strong wind, that wind itself can and push the vessel to away from the position. So to hold that rig in position, because we are drilling at a single point, right? So the well at the seabed is like a single point when we need to be centered at one point. So that is a very tight requirement from our side. So to keep the ship to keep the drilling rig in a static position, we need to have some forces which can hold it tight. Okay. So there is two methods for station keeping. That is, one is anchored mode and another is dynamic positioning. So for anchored mode, we have like anchors in place, like solid ropes and chains tied to the rig, and that is called the anchor mode rig, and another is dynamic positioning. In the dynamic positioning, you have like thrusters that is constantly like it is constantly there is a uh, uh, there is a like fan that is running, okay, with motor. So that gives the force to keep it stationary. And for that, we have like very complex computer system that is taking all the data from like seabed. It has like on the seabeds we have radio transponders, and from radio transponders it like all around the well there is like around eight transponders are placed on the seabed, and those transponders gives the signal to the rig, and rig system communicates with that to make the position, to know its position, like where it is, and based on that the forces on the thrusters are applied, so that the rig does not move from its location. Still, like it is not like the ship will be stationary at single point. There is some watch circle for this. So the ship, even with anchor mode rig also, we have watch circle for this. Like we have some tolerance where we can accept its movement. Like depending on the depth of the seabed, this watch circle is decided. So uh, uh, based on that, we define that green circle, yellow circle, and red circle. So if it is in green circle, it is okay. If ship gets into yellow circle, then all the forces will try to bring it back to the green circle. And if it cannot bring it back to green circle, then it may move in the red zone. And if it moves in the red zone, then we have to like disconnect from the seabed, like BOP will disconnect from seabed, like BOP and LMRP. There's two part of that. I will discuss further. So it will have to disconnect and it will have to move away from the location. Like if at all such a strong and environmental forces arises in at some point of time, or if there is some failure of anchor system, so there is mechanism to disconnect from the well so that anything is not broken or the well integrity is not compromised or any uncontrolled flow of hydrocarbon is not released on the seabed. So we have a system for that also. That is the contingency measure for a floating rig. So these are the challenges of a floating rig. So as I started in the first, the rig itself is not a stationary, the seabed is not a stationary, and to keep it in at a one point, we need a system. And even when we are like keeping it at one place, the heave motion is still there. The ship is still moving in up and down, and that movement is constant. It is not going away. And so for that, to compensate the heave motion, we have different system. But for station keeping, we have anchor mode and dynamic positioning. Okay, so this is just a video from YouTube. Just let me know if the sound comes there.
Sir, the sound is not coming.
So I think there is some issue with sharing sound is not coming now. Okay, I will reshare it. It's not asking me also. Okay. I will try once again. Let me know.
Yes, sir. It's perfect.
I think the anticipation is finally over. You know, you were excited to get on location and perform your job, do what the ship was built to do.
The Deepwater Atlas, really special ship, the first of her kind coming out, 8th generation. Things that a lot of people knows, the 3 million pound hook load, the 20K.
You've got excellent power generation, we've got so really it is the best, most advanced stuff in the world right now.
We're currently on the Shenandoah project. Once we finish these 4 wells, we'll swap out BOPs and come and complete them with our 20K BOP.
First in the industry, gotta lead the way.
It's just really rewarding to be part of it early before it left the shipyard, and then coming into operations, you can see what the ship can do and really put your hard work to purpose now.
It's a real good feeling to get it, to actually put it to work and see the years of hard work. And there were years of work before we got here, and to see all that come together and see the pride that people have in it is really cool.
Should take a lot of pride in being what is referred to as a plank owner. You know, you were one of the original crew members when it came out of the yard.
To see it operate in a fashion that it is supposed to run and operate is, yes, it's very, you can always look back and say, I did have a part of that.
A new rig, it's not like a new car. It's not, you pull up, drive it off and show it off. There's a lot of work into it. You can have all the technology in the world, but it takes the right people to really show it off. And I think the Atlas has that right people.
the camaraderie of everybody working together. And when I mean everybody, I mean from the engineering side to the drilling side to the marine side. Dude, that's a big thing about the Atlas right now, and I'm very proud to be a part of that.
I think we have absolutely assembled a team that's procedurally driven, safety oriented. I couldn't ask for a better crew.
This is our ship. We work for the best drilling company in the world, and it's our time to shine.
Okay, so you can have an initial look of a drill ship, right?
You pull out.
Yes, sir.
Yeah. So this is the in the previous video you could have some view of a rig, how it looks like, offshore drilling rig. Land rig you might have seen, but offshore rig going to offshore itself like takes too many trainings. So before you come into the industry, you like it, you may not you cannot go actually. You cannot go actually on a drill ship, because going offshore you need some training. Then only you can go offshore. Yeah. So you can watch some videos and be familiarized with what is deep water drilling. And if you see, then the deep water drilling is using the best of the technology, and like on the internet, like all the information is available, but only thing required is time. So I believe that is why I am here, so to have give you some idea that how the deep water drilling is working. Okay, so this is a description of a rig, a deep water rig, and so you can see for a rig, the basic equipments, the core philosophy is same, like we have to drill the hole from the subsurface, from the earth, okay, and remove the cuttings and deliver a usable hole for hydrocarbon production. But as I said in the beginning, for a floating rig, there are special requirements, and because it is offshore, so everything needs to be stored on the rig itself. There is no land where we will be storing anything else, so everything will be on board. And you can see in this the description of this. This is like drilling equipment. So derrick, hook, drawbox, compensator. So one part is compensator. Okay, so compensator is like drill string compensator. So it's like I will be talking further as well on this part. But compensator is something that that makes the makes the interface between the fixed seabed and the moving drill ship. So that is why we have drill string compensator. And top drive, tubular handling. Tubular handling is like for ultra deep water rigs. This is everything is mechanized. So like nothing is being done with the hands. So tubular handling is done by a special system that is called hydrotong. Yeah, and when you have like a seabed to the rig, you need to have some communication system, and that is riser. So to return the fluid from the well, we have risers, and mud pump is common. Another part is like BOP and LMRP. So BOP and LMRP is like a specific to deep water rig. Sorry, BOP is on the all rigs, but LMRP is the specific to deep water rig. So that is called a lower marine riser package. So LMRP also have one of the annular preventer, and LMRP BOP can disconnect from each other. So that is why we have LMRP. So that LMRP disconnects from BOP whenever there is a need, whenever there is some kind of emergency situation, then LMRP disconnects from the BOP. And for BOP handling also, BOP is a very huge structure. I will show you in the presentation. And then there is riser, there is tensioner, diverter, tree handling. So these all are like specific to the deep water rig. And then you have a station keeping system, that is thruster and DP system. So if you are interested, you can log into deepwater.com. That is the Transocean site. So from Transocean is like the biggest contractor for the deepwater rigs, and it is having the most advanced fleet. So I am not Transocean representative, but still I can say you this deepwater the Transocean is having the best of the rigs in the industry. So you can go and see on their site the fleet status, where they are operating, and what is the current assignments, what they are doing, and what the technological advancement that they have brought to the industry. So yeah, so this snapshot is from the Transocean rig only, and this is the first of it. Like this was not the video was for the like the first of the 20,000 psi BOP that has come to the industry. So that in the video they were talking about. Okay, so let us move ahead. Yeah, so this is a simplified sketch diagram for how the rig and the wellbore is connected. So from the down, you can see this is the 36-inch conductor casing, or the main wellbore, and above that is the wellhead, that is high pressure wellhead housing and low pressure wellhead housing. I will discuss it further. So wellhead is in two parts. That one is low pressure housing, and above that is high pressure housing. And from high pressure wellhead housing, the BOP is connected, and BOP is connected with riser, and the riser comes up to the surface. And on the surface, we have a slip joint, that is telescopic joint, and the telescopic joint is like two concentric tubes inside. So this is a moving system. So whenever the ship heave motion is there, so telescopic joint, the one part of the telescopic joint is stationary, and another part that is attached to the rig moves up and down. So you can see the tensioner ring. Tensioner ring is the part of marine riser tensioner. So this whole structure, the BOP and the risers, needs to be hanged with some upward force to keep it in position. So that is done by the marine riser tensioner. So that tensioner ring is, I will talk about it further as well. So just you can see the schematic of like how it is connected, how it looks like, the drilling system from the wellhead to BOP to riser to tensioner ring to the rig. And on the right hand side, this is the drilling riser joint. So these risers looks like this, and this is BOP. So if you have seen any land BOP, have you seen any BOP? Yeah, Vijit, you can answer.
Sure.
Have you seen BOP, blowout preventer?
Yes, sir, the
Yes, sir.
onshore ones we have seen.
Onshore ones you have seen, right? And this is the subsea BOP. So can you check the scale of it, like how it looks like? So with the onshore and offshore, the BOP, onshore BOP is a very small structure, and for subsea BOP, this is complete a big like a huge thing. This is a complete like it looks like a big house. So, but you can see on the center only there is BOP, and on the right side is the BOP card that moves the BOP from like uh, parking position to the center position. So the middle one, that is the yellow part of the thing that is in the very center, that is only BOP. Other things are the card that helps to move the BOP. So this is and you can see a very big opening. This is the opening to the sea. The rig is open from the middle to the sea, and from that opening only all the operation of lowering BOP, lowering risers, and everything happens. So that is called moon pool. So this term is important. That is moon pool. So moon pool is an opening in the middle of the rig, in the center of the rig. And from that to that opening, all the operations of running BOP and risers happens. So right now this BOP is at the card, and either it will be moved to the center and a riser joint will be connected, and then with the riser joints it will be continued to be lowered. So this is a subsea BOP. Okay. And what are the functions of a BOP? You already know that what does the BOP does. So BOP in case of any failure of wellbore barrier, like if the hydraulic fluids is not able to hold the formation from coming inside, then we have to close the BOP. So that is the normal function of a BOP. But other than that, there are another other functions as well in the BOP for the subsea BOP. This is specific to the subsea BOP. So there is one emergency disconnect sequence. So there is a button on the rig floor, and even at the tool pusher office, and even at the uh, bridge. Bridge is the central command of the drill ship, the marine side of that. That is called bridge. So from bridge also they can, like, if the captain see any problem, then they also can initiate this emergency disconnect sequence. So emergency disconnect sequence is manually activated. It is not automatically activated. It has a button has to be pushed, and if that button is pushed, then the disconnect sequence starts and the wellbore is secured and LMRP is disconnected from the BOP. So there can be many situations where we have to push this button, and EDS sequence is specifically decided based on what kind of tubular is in the hole. So that you will learn later only. But first, just need to understand that there is EDS sequence. We call it emergency disconnect sequence. There is another deadman system, and deadman system is like if you are running the BOP to the subsea, to the seabed. So we have like electrical and hydraulic lines for the control line, for controlling the BOP, for operating the functions of the BOP. But for control system, there is two pods, yellow pod and blue pod, and yellow pod. So if like both the pod, if there is a failure of the both the pod, then the deadman system will automatically activate, and deadman system will secure your well and disconnect the LMRP from the BOP. So if there is electrical system failure, if there is a power blackout and there is no hydraulic power also to operate the BOP, then the system assumes that there is some emergency, and it activates the sequence on its own, and that is called deadman system. And another is auto shear. Auto shear is like if there is a drive off situation, like your rig moves away from the location due to any reason, and there is a chances that LMRP gets getting disconnected. In that situation, this auto shear system activates, and it will shear off the drill pipe. It will close it will secure the well and disconnect the LMRP. So this is the auto shear system. So these are some specific functions to the subsea BOP. And I will show you this video. This is I was talking about the marine riser tensioner system. So here in this video, actually EDS sequence is being tested. So I will show you in the video how what happens. Okay, so you cannot see what is happening downhole, what is happening at the BOP level. But if you can see in the starting, it was moving like it was moving up and down. But at one point, it just come up and didn't go down. So at that point, EDS sequence has been activated. the emergency disconnect sequence was activated, and because this tensioner system is charged, so if there is a disconnect, then it will come up with the force of the lifting system. So it will the LMRP will come up. So that is how it is being it is it is happening here. So the riser tensioner is coming up, and LMRP has already disconnected from the BOP. That is not visible in the video. So, and in this video, you can see this the moon pool area, and you can also see the marine riser tensioner and the slip joint. The okay. So this is the slip joint that you saw in the previous video. That we call telescopic joint as well, or slip joint. And Riggs heave motion and static riser joint is interfaced using slip joint and MRT system. So, so the where the marine riser tensioner is taking the weight of the riser, and you can see that there is a continuous movement between the two between the interface. So because the BOP and the riser is everything is static, BOP is not moving, the wellhead is not moving, right? So because wellhead is at the seabed, so your earth is not moving, only the sea level is in the motion. So that is how because the ship is in motion and your BOP and riser system is static. So that is why we have a telescopic joint to make the interface of a static system and a moving system. And on the right side, you can see these lines comes to these tension compensator system, marine riser tensioner system. That is from where you get the power to pick it up and compensate the motion. So this is the tensioner system that we have on a subsidy. And these are the riser joints that we were talking about. So riser, I already talked the what is riser. So you know that riser is something that is above BOP and comes up all up to the surface. So riser is 21 inch in OD, and generally this is the general size. OD is 21 inch and ID is 19 inch. So this is a very big bore size for the well. If we are drilling a 8.5 inch hole, and if you are drilling like 3,000 at 2,000 meter of water depth, and so like 2,000 of meter of your return path will be a very big hole that is 19 inch size, and below that it will be only 8 inch size. So if you know that to lift the cuttings, you need some velocity. So in the larger size, larger bore, like the velocity will reduce and the cutting may start to fall. So this is the challenge for the subsea system, and that is why we have a booster line as well in the riser. So that booster line is attached to a mud pump, and mud pump gives circulation above the BOP. So it increases the velocity in the riser section. And in the main hole section, that is only 8.5 inch size. So there you don't need high velocity. No, you need high velocity, but you don't need high flow rate. So from the drill string, minimum 500 to 600 GPM is pumped from the drill string, and the rest of the circulation is done through the booster line. So riser serves multiple purposes. You can see there is only one way with which we are connected to the seabed, and that is riser. So riser, there you can see there is for the riser there is like one main bore, that is big bore, that is from where the mud returns are coming. But apart from that, you can see there is 5 lines on this. 5, that is called rigid line. That 5 metallic pipes are there, right? So you can see. So those lines are choke line, kill line, booster line, and rigid conduit line. So conduit line is for communicating the hydraulic power to operate the BOP functions. To operate the BOP functions, we have rigid conduit line. So we have different kinds of control system for BOP. For ultra deep water, generally this is rigid conduit line only. But for some shallow water floater rigs, we have hoses only, hoses as well. That is, we don't have a conduit line in the riser. That hydraulic power is given by a separate hose, like rubber hose, you can say something like that. So, but for ultra deep water, we have rigid conduit lines that provides the hydraulic power for operating the BOP functions. So, choke line, kill line for a subsea system, subsea BOP, choke and kill line are interchangeable. So, like there is no as such very big difference between choke and kill line. You can interchangeably use any of the line as a choke line and a kill line. And choke line and kill line are are activated when you will close the BOP and want to take the return through choke line or kill line. Then you for like well killing purposes also choke line and kill line are used. So choke and kill lines are used for well killing purposes. Booster is above the BOP and it is used to circulate the riser, and rigid conduit is for BOP control lines, providing the hydraulic power to the BOP control functions. So these are the functions of a riser joints. Riser joints is not a simple piece. You can see this is like a complex function that is being served by the riser. Okay, so as is previously shown you telescopic joint. So this telescopic joint is to compensate the motion of the riser. Likewise, we have a drill string motion compensator. So this is for compensating the motion of the drill pipe. So if you're drilling with a drill string, so and your ship is in motion and you touch the seabed, sorry, you touch any formation, right? So if your ship is like coming up and down, so it will give very hard bang on the surface if you do not compensate the ship motion, ship heave motion, and ship heave motion is very strong. The full the power of heave is very strong. It can break anything. To compensate that to have uniform weight on bit, we have the compensation system that is called drill string motion compensator. The basic principle of riser tensioner system and drill string motion compensator are same only, but these are the two parts where we need the compensation for the drill string and for the riser. So in this video also I can show you like how it is. Yeah, so this is a simplified diagram, just to have a feel of it. The whole ship is moving, you can see in the video. And for drill string motion compensator, we have two systems. One is passive heave compensator and another is active heave compensator. So passive heave compensator works only when there is some obstruction, like if the drill string touches some surface and like it starts to like it gets some obstruction, then the passive heave compensator starts to act. Like it will not, it will just act as a shock absorber. So it will not give a hard bang on the surface, on the seabed or on any formation wherever it is. So passive heave compensator is for that. And we have like advanced system that is active heave compensator that with the sea state it anticipates that how the ship is going to move, and with that it gives the auto compensation. So that is active heave compensator. So, like previously, most of the rigs had passive heave compensator only, but now the ultra deep water rigs and many rigs that is coming today are having active heave compensator as well. And this compensator, drill string compensator, is required for various purposes. Even when you are running the BOP on riser, that BOP is also before the riser tensioner are activated. Before that, MRT is connected. The riser is being run on the blocks only, traveling blocks only, and that block is compensated using drill string motion compensator. And when we are latching the BOP to wellhead, at that time tensioner is activated, but full load is not given on tensioner. The some load is there on the drill hook as well, on the traveling block as well. So this drill string motion compensator helps to latch to a static system and a dynamic system. So this motion compensator is used for various landing operations of BOP to wellhead, casing and hanger on wellhead, and various other operations where we have to land on wellhead, or you have to set a packer in the casing. So whenever there is a static system and a dynamic system, then you will need the motion compensator. That is specific to the deep water drilling, because when you go for jackup or a land rig, you do not have something that the ship itself is moving. Your rig itself is moving. You do not have a system like that on a jackup rig or a land rig. But for a deep water rig, floating rig, we have these challenges. Okay, so this is another video. So I will just I will not play fully.
Explain our planned activity be avoided or minimised. Woodside also prepares environment plans that detail how drilling will be undertaken and obtain approval from relevant regulatory authorities before drilling commences. Wells can be drilled by either a drill ship or a drill rig, known as mobile offshore drilling units or MODUs, depending on water depths and other factors. To ensure the safety of other marine users, vessels not involved in drilling should stay at least 500 metres away from the drilling location while in operation. This is called a safety exclusion zone. Once the well is complete and drilling infrastructure is removed, marine users are generally free to resume normal activities. While technical differences exist, the process for drilling all offshore wells is similar and take place in several stages. Before any drilling, a remote-operated vehicle, or ROV, is sent to assess the condition of the seabed. A hole is then drilled into the ocean floor using a large diameter drill bit, and steel pipe called a conductor is installed, providing the well's initial structural support. A smaller drill bit is then lowered through the conductor to drill the next section, which is called the top hole. Once it reaches a predetermined depth, more steel pipe called casing is installed, supporting the newly drilled hole. Cement is pumped through the casing, moving between the casing and the drilled hole, securing it in the ground. The cement is allowed to set before drilling continues. Before drilling deeper, a blowout preventer, or BOP, is installed on top of the well. The BOP is a large, specialised safety device used to seal, control and monitor wells to prevent uncontrolled release of fluids. After the BOP is secure, a smaller drill bit is lowered into the hole to drill further, and more casing is cemented into the ground. This step is repeated until the well reaches a specific depth where the targeted reservoir is predicted or known to.
Okay, so that was like some view of how ROV is working and how the BOP is lashed to the wellhead. So just to have a feel of it. Another important technology for the deep water drilling is subsea wellhead. Subsea wellhead system is is very different from what you see onshore or other wells. So subsea wellhead system is having two parts. There is one is low pressure housing and another is high pressure housing. High pressure wellhead housing and low pressure wellhead housing. So low pressure wellhead housing is run with conductor casing like 36-inch casing or 30-inch casing. So you, on the top of the 36-inch casing is low pressure wellhead housing that we run. And after that, we run the high pressure wellhead housing that is run with the 20-inch casing. And the high pressure wellhead housing goes and lands on the low pressure wellhead housing. After the high pressure wellhead housing is lashed on the low pressure housing, BOP is run and then BOP is lashed to the high pressure wellhead housing. Up to this point, BOP is not connected and all the drilling is being done riserless. So after the high pressure housing is lashed to the low pressure housing, the further casing will come with casing hanger, and sequentially the casing hanger will land in the high pressure housing. So this is called integrated wellhead as well. So all the casing hangers are landing inside the high pressure wellhead housing, one after the another. And to seal off that angular area for the hanger, we have the seal assembly. So each hanger is the seal assembly is energized and annulus is sealed. So I hope you understand what is annulus. So it is outside area of the casing. So if you land the casing hanger in the wellhead, so, then the annulus area needs to be sealed, and that is done with the seal assembly. So seal assembly are the part of the wellhead. And you can see, just to repeat, this is low pressure housing, high pressure housing, casing hanger, and then the BOP will be lashed to the high pressure housing. Yeah, any question, anyone, you can ask in the middle also, no problem. Yeah, so just we talked about the low pressure and high pressure housing, wellhead housing. So up to the installation of high pressure housing, all the drilling is called the top hole drilling. So this top hole drilling is riserless drilling of top hole. So there is no riser, no return to the surface. All the everything you pump is going to the seabed. So the steps of top hole drilling is we drill a 42-inch hole and lower 36-inch casing. This is one way, but more frequent way is you run with a 36-inch casing and a 26-inch bit that is coming just outside of the casing, and you jet the 36-inch casing into the seabed. You pump at a very high rate, and because the upper soil is very soft, so you can jet the 36-inch casing up to like 70 to 90 meter below the seabed. That is called mud line also. So you can jet the 36-inch casing up to like 70 to 90 meter below the mud line, and you give some time for soaking of the casing. And we have a drill ahead tool uh, in the running tool system. So you can just wait for soaking and you can continue drilling 26-inch hole from that point itself only. So one point that you may not have noticed, that for the ultra deep water wells, we have like 2,000, 3,000 meter of water depth itself. So to trip that 3,000 meter of drill pipe, it takes too much time. So 3,000 meter wells are like on the land wells. 3,000 meter is like a very deep well. But if you have like 3,000 meter of only water, so you tripping time is very substantial. So if you save some time in that, and the cost of rig is very high, so that we have a system for that. Like you can just wait for soaking of 36-inch casing, and you can start drilling the 26-inch hole from that point itself. And you drill the 26-inch hole and then pull out the BHA and then run the 20-inch casing with high pressure housing. So just I talked that while drilling top hole, cuttings are returned to seabed. Drilling fluid that does not return to rig and are lost at seabed. So if you are pumping at whatever rate, but you cannot supply so much of drilling fluid if everything is not coming to surface. So for top hole drilling, mostly seawater is used with some gelation, some bentonite is used, but mostly it is seawater with which the top hole drilling is done. So seawater is abundant at sea. You don't have to worry for that. But for all other thing, you have to worry for, like, if you, even if you need drill water, that is called water. That is not seawater, right? So for even for water, you need to have like ship comes from the shore and it brings water for the rig. The, there are systems to like prepare water on board as well, but still that capacity is not enough. So most of the time, the ships are bringing the water for the rig. So water, beride, all the chemicals. So everything needs to come from shore base, and that has to come from the supply vessel. And supply vessel, it will take time for coming if you are in a remote location. So it takes time. So these are the logistical problem as well that is specific to the deep water drilling. And many a times you are drilling in a frontier areas that is unexplored area. So at that point, there is no support system on that area, and there is nothing that is developed. If you are drilling in a Mumbai high, so you have like so many platform and everything all around. But if you are drilling in a remote location, then yeah, like you are the only one who is there. Yeah. So this is the low pressure housing that is being run through the moon pool. And so the this is the low pressure wellhead housing, and that is run with the drill pipe. That is landing string. When you run the drill, low pressure housing, and you can unlatch and pull out the landing string. That is the general procedure for running all the casings as well. Intermediate casing, production casing, and liners. So after you drill the top hole, the other operations are very similar to the normal wells. Almost similar, still not the same, but it is like when you connect the riser to the riser and BOP to the rig, and then you have the return system also. Your pumping and everything is coming to surface through the riser. So it is almost same. So after the high pressure housing is latched on the low pressure housing, the further casing hangers are landed on the high pressure housing. So that is what I'm talking here. And liner hanger, you might be knowing liner hanger is what is it is that does not come all up to the wellhead. It is like there is some overlap in the to the previous casing, and it is hanged to the casing itself. So that is called liner. And wireline logging is the general procedure, like for like in or for the each hole you drill, you record the wireline log, and then based on that you evaluate the formation, evaluate the petrophysical parameters of the formation, and then for the exploratory drilling, this is very important. Even for development wells, also we record the wireline logs to confirm that whatever we thought is as anticipated. So the wireline logs logging is done, and the deep water is most of the times for deep water we are doing exploration. So wireline logging is very important for us. That is gives the result like what we have got, what we have drilled, and what we expect, whether we need to test the well or not. So we drill the well to find hydrocarbon, and to establish that there is a hydrocarbon, we need this wireline logging. Okay, so for drilling part, this casing pressure test. So every time you run the casing, you need to test the casing that the casing is holding. There is no leak in the casing. So you test the casing by pressurizing the casing. By there is a drilling fluid inside the casing, and you give pressure. You pressurize that system from surface. So that is called positive pressure test. And there is another name is negative pressure test or inflow test. And this inflow test is very important. And inflow test is done by pumping a underbalanced fluid in the well and monitor if there is any return that is coming. So it establishes that the reservoir pressure is not communicating with the case, like it is not coming inside the casing. So if you have run the casing, cemented it, then you need to inflow test the casing so that to ensure that there is no flow from the direction of flow. That usual direction of flow is from the reservoir to the casing, to the well. It is not the other way around. That is what we establish in positive pressure test. We pressurize from surface. So that is opposite to the direction of flow, but that is also a way to establish the integrity of the well. So that is positive pressure test, and the negative pressure test, that is called inflow test as well. So positive pressure test generally is done to the maximum expected differential pressure in displacement to gas scenario from next open hole section. So if you run the casing and you are going to drill the open hole after that. So if you drilling the open hole and there is some gas, if there is a blowout situation and all the well is filled with gas. So even if you close this with BOP, but if your casing burst in that situation, then it does not serve the purpose. So your casing needs to uh, hold that pressure, and that is what we establish by doing the positive pressure test. So this is the specific problem for the deep water drilling. This is one part is shallow gas that I already talked about the top hole drilling. So up to the surface casing, that is 20-inch casing, we are drilling riserless. So there is no BOP. There is nothing to hold the pressure. If there is some pressure, some high pressure zones are encountered in the top hole section, then there is no mechanism to contain that because we do not have a BOP there. All we can do, maximum we can do is a pump high weighted mud in that well. But that is the only defense we have. And if at all, if like a very high, very large pocket of shallow gas is encountered in the top hole section, when we are doing drilling riserless, then there is a possibility that the even the buoyancy of the water may go down, and there is a chances of sinking of ship also. So that is a very rare phenomena, but like that may happen. Like if there is like shallow gas, very large pocket of shallow gas is encountered, then the only option that is left with the rig is to move away from that location, because you cannot contain that immediately. If you can contain that, you could have already done that by pumping the high weighted mud. But if it is not possible, the ship has to move away from the location. So that is called the shallow gas. And for shallow gas also, we sometimes we also drill the investigative hole first. A small diameter hole first we drill, and we see if there is any gas in that section. If there is no gas, then only we go for the top 26 inch, 36 inch drilling and 26 inch drilling. So that is the shallow gas. That is one hazard. Another is the gas hydrate. So gas hydrate is on the figure you can see the temperature gradient. You just focus on the temperature gradient in seawater. From the surface, the temperature, if you go down the seabed, if you go down from the surface of the sea, the temperature is falling. And when you hit the sea floor, after that, the temperature will start to rise again. So this is a very peculiar for the sea, offshore wells. And if you have a like sufficiently high water depth, so the temperature goes up to like 4 degree, 2 degree Celsius. So at that low temperature and high hydrostatic head of the seawater, this is a suitable zone for stable zone for the hydrate formation. And if you know gas hydrate is like formed when methane and water comes into contact at low temperature and high pressure. So water forms a bond, and within the water, this is a gas hydrate is ice-like a structure, and in the ice lattices, this methane gas is entrapped. So very high volume, high concentrated volume of gas is entrapped in the gas hydrate. And gas hydrate is something that ice that burns. Like you can burn the ice and it will start to burn because of presence of methane. So that is one part that we are also looking for, like gas hydrate as a alternative energy sources, but mostly we have not succeeded till now. But uh, gas hydrate is a very big challenge for the deep water drilling actually, because if due to this situation, if some plugs gets formed, then circulation is seized, and you land up in a very big trouble. So generally, when you have a kick, then hydrocarbon is coming up. So hydrocarbon is there, low temperature is there, high pressure is there, your BOP is closed. So all the situation makes it convenient to form the gas hydrate in the choke or kill line. So to prevent that formation, we need to ensure that water-based mud is not being used, or if you are using water-based mud, then there is sufficient inhibition that needs to be there in the water-based mud so that the gas hydrate formation is avoided. So for deep water, gas hydrate is a challenge only. This is not helping any way. So it can plug your choke line or kill line. And another thing is that sometimes the gas also comes from the outside of the casing, the 36-inch casing, and that gas can come up and make a hydrate plug in the area where the BOP latches to the wellhead. And if that plug is formed, then you cannot unlatch the BOP. So you're latched to the wellhead and you cannot unlatch that from wellhead. So that is a very difficult situation where you're locked, kind of locked there. But because we are working in the industry has found the solution for that as well. So we have like pumping glycol, methanol. By pumping regularly glycol, we avoid the formation of that, and we also have the hydrate uh, like uh, uh, in like there is a mechanism to stop like the hydrate is not this hydrocarbon is not allowed to come inside the latching area. So that is how it is ensured that such challenge does not arise. But in a subsea well where you have like 1,000 2,000 meters of water depth, uh, uh, gas presence of gas is always there. Like most of the time, there is some gas that is coming from the outside of casing, and so it is the gas hydrate problem is very real for deep water. Another part is like well testing. So if you drill the well, you need to test it. Test it means like we test it. That is called drill stem testing. So that we do for all other wells also. But because in deep water we are mostly doing the exploratory well only. So well testing is the integral part of deep water drilling. So the final result comes from the well testing only. So, but if when we are testing a well, so we already discussed that the ship is in motion, ship can disconnect anytime. So and we are isolated at some remote locations. We are there, and all the hydrocarbon is coming to the rig, and that is where you live. All the like 100, 150 persons are staying on that rig, and hydrocarbon is flowing on that rig. So there has to be a foolproof method to contain the system, contain the hydrocarbon whenever required at any point of time. With a click of button, everything should shut down so that we can handle emergency situation. So for that, for well testing, we have uh, different valves. That we can set the well downhole at the reservoir level, at subsea level, at surface level, at the flow head level. So there are multiple valves that is there, and most of the valves can be operated remotely as well. So this is a very safe system. There is nothing like, although this is very risky, but industry has already found solution for that. And even like we were talking about the disconnect sequence. So for the subsea landing string also, it can disconnect at the subsea level. And we have for the test string, we have the subsea test tree as well. So that subsea test tree goes and lands inside the BOP. So this is a very complex system, and you need a very detailed analysis, detailed study for that. But just to give you an overview of what we do in well testing. And when you drill the well, then you before leaving the well, you need to abandon it so that hydrocarbon flow is not there when you leave the location. So so when your drilling completes, then we place the different cement plugs, and after that the BOP is unlatched from wellhead, and look, we can leave the location. We ensure that there is no hydrocarbon that can flow from well by placing of cement plugs. So that is called abandonment. And this is the subsea field development, how it looks like. So most of the times we are doing exploration, but if we get success, we get success in then exploration, then we drill the appraisal wells. And with appraisal wells, if it looks like that economics is favorable, we can develop the field. So to develop the field, we need to have a separate planning. And subsea field development is a whole new domain and a whole big domain. And multiple companies are operating, and this is the very advanced system that that industry has already found the solution for. But this is something like multiple companies are working in this area for subsea field development. This is a very huge teamwork, and that what we do, that this is the final outcome that we desire. And this whole operation from drilling to development to getting oil and gas, it takes like minimum 5 years, 10 years. It takes that much of time from exploration to exploitation, right, to get the hydrocarbon on surface and to get the hydrocarbon at economical scale. So this is the final outcome of the deep water drilling, if at all we are successful in that. And to develop that, we need the flow assurance. Flow assurance is you need to ensure that there is no hydrate plug is forming, or if there is oil, then you need to pump some chemical PPD and everything, so that the lines are not choked. And you need some compressor station, some pumping station as well on the seabed to pump that fluid to platform or land area, onshore area. You may have to make decision for whether you need to install a production platform, or you have to bring FPSO, or you need to plan your well completion strategy, whether you need to do sand control or not. So this is a whole new domain. So this is the all that I had today. So now we are open. I will stop sharing now. Yeah, Vijay, my voice was okay, right?
Yes, sir. Your voice was perfect.
Okay, thank you. Yeah. So any question,
Priyanka.
anything, then I can take it, no problem.
Sir, I would like to say, whoever has the question, please raise your hand and we'll take it one by one. Sir, we have a question from Abhinav Raj. Abhinav, you can unmute yourself and ask the question.
Sir, you did discuss about the various kind of equipments, like specifically to offshore that we have for the safety management. But like over the years, we have seen incidents like the Deepwater Horizon that have highlighted the risks associated with deep water drilling, basically. So could you share how far the industry has progressed in terms of safety technologies or some innovations, regulations, best practices since then? And in your experience, have you ever felt that due to some profit pressure, safety was not given that kind of attention it should have deserved? that operations were left almost to its fate.
Yeah, no, yeah. Thanks for the question. Yeah. So this basically, if after Deepwater Horizon, the industry like most of the times when you are working perfect, nobody gives an eye to you. So there is so many like associated government function, everybody. Nobody knows. Okay, just 1 second. I will just come back. Yeah. No. So the best way for us is to like work in silence so that nobody notices us what we do. But as you know, in the Deepwater Horizon, what happened. But it was not the failure of the system. It was the failure of the analysis and all the taking it light. You might have seen the video analysis also, what has come in the conclusion. So it was some some hurry and something like that. So most of the time that we see the incidences in the industry is because of that only. Taking the shortcuts. It is not because of the not non-availability of the technology, because technology is already there. But I will say from the deep water perspective, deep water safety system is very, very, very stringent. Like even for PSUs like us, like deep water, the best of the safety is in at the floater rig only. So that I can say, so most of the time it is human error only, and technologically we have reached the level where such incidents should not happen. Yes.
So,
So, sir, we have a question from Arima Parihar, ma'am. Ma'am, you can unmute yourself and ask the question.
Sir, I wanted to ask, like you mentioned about well testing. So, are there any major differences in well testing between offshore and onshore environments? We study here like about well testing and well performance, but I think that it's majorly focusing on the onshore environment. So, are there any differences?
No difference. Theoretically, there is no difference. We want to establish the same thing. With well testing, we want to know how big is the reservoir, what is the flow potential, and all. So objectives are same, but the scale is different and the technology is different. Because you have a very different technology for the deep water. You have something extra that is in the form of landing string that goes in the riser. So above the BOP, the system is different, and apart from that, other things are same.
Okay, sir.
So now, sir, we have a question in chat from Prem Kumbhare, sir. He says, sir, offshore reservoir are generally tight reservoirs. So what kind of stimulation procedure we can follow?
Actually, if it is tight reservoir and we need to stimulate it, so everything adds to the cost. And if at all the reservoir is like that, many a times the we might not be stimulating it. But because when we go offshore, we are looking for something big. That is something that is flowing on its own. Do not need to stimulate it. But in terms of a stimulation, sometimes we have to do the sand control and all. So the sand control itself is like when you have loose formation. So there is not this is not the tight formation. So if you have a tight formation and you have to hydrofrac, very rarely hydrofracking is being done in deep water. I would say that in my knowledge, hydrofracking is like it's not very common for deep water. Yeah.
Okay, sir.
Sir, I
Thank you
would
so
like to
much.
add on to this. If our reservoir is carbonate reservoir, so like acidization procedure we can follow, right? For stimulation.
Acidization and all we can do for sure we can do, but that is what I'm telling. Like if you have to do anything, you need a rig, and that adds to the cost. If it makes economic sense because the reservoir and everything is same, like below the seabed, most of the things are same except that like pore pressure fracture gradient, like for ultra deep water fracture gradient is less. that is different thing. But other than that, like the theoretically, all the other stimulation techniques are same. So, but only difference is the economics. If it makes economic sense, then we can do all the things that we are doing on the land on any other wells. So deep water, I do not think it is a very common practice. For shallow water on jackup rigs, we are regularly doing it. But the deep water, we can do if economic supports. Yeah, yeah. For everything, you need to run the NPV analysis and IRR analysis, that how much return you are going to get from that. And if it makes sense, you can do that.
Okay, sir.
Sir, I would like to ask that what are the key considerations when planning and drilling of completion of subsea well?
Yeah, sorry, can you repeat?
Sir, like what are the key considerations when planning the drilling and completion of a
Okay,
subsea well?
okay. So the key consideration for the subsea wells are basically the same for the all other wells as we drill. But as you can see, for subsea wells, it will be completed on the seabed, and from seabed there needs to be a flow line needs to be connected, and the control of the Christmas tree is with the umbilicals, hydraulic and electrical umbilicals. So for well design, basically for the subsea, like because of the very narrow margin between pore and fracture pressure, you have challenges for that. Like for the ultra deep water and deep water wells, you have like you get a very narrow margin for pore and fracture pressure. So you may have to run multiple liners, multiple casings also. So, but the principles remain same that we do for all other wells.
Okay, sir.
So does anyone else have a question? Yes, sir. We have now got a question from Imran Nazir, sir. He has asked, what are the difficulties of doing DST, RFT tests in offshore as compared with onshore wells?
DST, there is no, I would say, I will not say there is any difficulty or anything, but you need to have a system. Like for a landing, like I already said that below the seabed, the system is same. Above the seabed, in the risers, you need to have different valves, and those valves needs to be like you need to disconnect from the subsea test tree level. You need, if you when you disconnect, you have a lubricator valve in the landing strings, and you have a retainer valve in the landing string. So some additional valves are there. And when you are at surface on the rig, we have a diverter system also. So for diverter system to activate, you have a RSM, we call riser sealing mandrel, we call it. So riser sealing mandrel is on the seabed, sorry, on the rig floor, across the rotary tables. So this is all the differences are in the landing string only, and other part there is no such difference other than that.
Okay, sir. There is one more question. Sir, could you please brief on the managed pressure drilling technique in deep water wells?
Managed pressure drilling in deep water wells is like challenging, because you will have to have a very huge volume of like if we are going for a, it depends upon like what is the requirement. But to manage pressure drilling, if we need to do managed pressure drilling in deep water, then you have to have like a rotating control device in the riser just below the your telescopic joint, and your riser will be pressurized to the pressure, whatever is the pressure required for managed pressure drilling. So again, the principle remains same, but challenges are different, because you have riser that you generally do not pressurize. Riser is generally in the normal pressure, but if you are doing managed pressure with within a deep water system, so that rotating control device is just below the sea level. So from there you need to close it, close on the drill string in the riser. So that is how we do for the managed pressure drilling in the deep water.
Okay, sir. Thank you. And sir, I think we will take the last question for today. Devanshi, you can unmute yourself and ask the question.
Good evening, sir. I am Devanshi Joshi, a first year student. My question is that with advancement in technology, how is digitalization supporting safer and more efficient offshore drilling today?
Yeah, basically with digitalization, we can see things more clearly. We can make decision very fast. And today, like in all the aspects, this is being used right from safety, from safety, we are creating behavior analysis. What is going on? We are creating trends from the machinery part, and we are analyzing reservoir in a better way with very advanced computing power. But we should also remember that this is not something new for the oil and gas industry. With the seismic and all the interpretation, this is happening from from the beginning of the availability of this system. So we are the first to use the supercomputers. So oil and gas industry has always been using this technology right from the beginning itself. But yeah, with that technological advancement and industry is very fast, accepting these measures also. And we are as the other industries are innovating, the oil and gas industry is innovating at the same pace, I would say. Yeah.
Okay, sir. Thank you so much for the answer. Can we have one more question at the end?
Yeah, no problem. Yeah.
Sir. So there is a question in the chat. How do we conduct downstream or transportation of produced fluids? And do we have processing plants on such platform?
Yeah, it all depends upon like where you are doing. Like if it is ultra deep water, you cannot have a platform there. So you need to bring it to some cellular location, then you can install the platform. So it is very specific custom build for the field that you are going to develop. And in the subsea, there is innovation that is happening every day. And that innovation can be like a specific to your field also. Like if you have found a very good, very big reservoir, then all the companies can come sit together and decide how to pump for how to take this hydrocarbon to the onshore. So that can be custom built also, and we have like subsea pumps, subsea compressors also. So it is very much custom, I would say, customized because it is specific to the field, which field we are developing.
Thank you so much, sir, for such a detailed and enriching session and for patiently answering all our questions.
Yeah, thank you for inviting me as well. So I also have a great time interacting with you all. So thank you all. You can. It's a good initiative that you have taken.
So we have now reached the conclusion of today's session. On behalf of everyone here, we express our sincere gratitude to you for sharing your time, your knowledge, and your experiences. Thank you so much, sir, for being a valuable guest here. I hope we can collaborate more in the future.
Yeah, thank you, Abhijit. Thank you. So I can leave now, right? Okay. Thank you. Thank you,
Yes.
everyone.
Thank you, sir.
Thank you.
The meet has finally come to end. You all guys can leave now.